In business, it is just as important to know when a plan might fail as it is to know when it will succeed. Since many businesses are modeled using mathematical equations, we can use math to help determine when equations' derivative may fail to exist. Hi, my name is Tom Atwater, and that's what we will be discussing in today's lesson. Let's start by establishing when a derivative may fail to exist. A function will not have a derivative at the point P, which is a comma f of a, where the slope of the secant lines which fail to exist. And so f of x minus f of a over x minus a fails to approach a limit. Let's look at some examples of where they fail to exist. Let's start with a corner where the one-sided derivatives differ. So we take the function f of x is equal to the absolute value of x. If we draw that graph, remember that graph starts here at 0 and goes up to the right with a slope of +1 and goes off to the left with a slope of -1. So what happens is we have a corner right there at x equals 0. So that's an example of where the derivative fails to exist. Let's take a look at the next one, which is called a cusp. A cusp is where the slopes of the secant lines approach from one side, and from the other side, they're approaching negative infinity from one of the sides and positive infinity from the other side. And so let's take a look at this function, which is f of x equals x raised to the power 2/3. The graph of this function looks like this. And you can see that what's happening is right here, we're getting a cusp. And you can see that the slopes are approaching negative infinity in that case. And if I look at the other one, they would be approaching positive infinity. All right, let's look at a third example, a vertical tangent. So that's where the slopes of the secant lines approach negative infinity or positive infinity from both sides, as in the function f of x is equal to the cube root of x. This function looks like this. And so in this particular case, we're going to get a vertical tangent right here. And so we would have, again, a failure of the derivative to exist. And the fourth example that I want to take a look at it with you is discontinuity, where one side of the one-sided derivative is just non-existent. An example might be the unit step function. So let me draw that for you, where it comes in, and there's an open circle at the -1, and then it picks up at +1 and continues out in a horizontal line. Once again, what you see happening here is that there's a jump, right? There's discontinuity here, and so the derivative does not or fails to exist. So that's our 4 examples or 4 definitions of where that can happen. Now, let's try an example. Let's take the function that's shown below fails to be differentiable at x equals 0. Then tell whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. And so we have y is equal to tan inverse or arctan of x, and x cannot equal 0. And y is equal to 1 at exactly x equals 0. Now, since we want to differentiate at x equals 0, and we know that at x equals 0, y is equal to 1, because that's our definition, but the arctan, or the tan inverse of 0, we would get the value 0. Right here, the arctan of 0 is 0. So therefore, the problem is discontinuity. This one gives us 1. This one would give us 0. All right, great. A good way to think of differentiable functions is that they are what we call locally linear. That is, that a function approaches the slope of its tangent line as you get closer and closer to a specific point, for instance, point A. So let's look at this graph and see what's happening. We're going to take the function f of x is equal to x cosine 3x. And that's the graph right here. And looking at the graph, there isn't anything too special about that. But as we begin to zero in on the point 2, 1.9, so looking over here, we're starting to zero in. Look what's happening to the curvature of the line here. Compared to what we see over here, we can begin to see that it's less curved. And when we look and actually zero in even closer, so you can see we're using a window that gets us even closer to the 2, 1.9, it's getting even straighter. And so that's what we mean to say that it's locally linear, that when you get and zero in on a specific point, you can see that it's approaching a straight line. Some graphing utilities can approximate a derivative, like your graphing calculator, and it does it numerically with fairly good accuracy at most of the points in the function's domain. Let's see how we might actually do this. The calculator sets up what's called a symmetric difference quotient using a really small value for h. It's very similar to taking the limit as h goes to 0. Now, this is done with a function which is abbreviated n-dir, which of course is the function's derivative. And it takes 3 arguments. So let's look at this right now. It takes the function, which in this case is x cubed. It takes the variable. We have to tell it that the variable that we want the derivative with respect to is x. And then the third argument that it takes is the point at which we are looking for the derivative. So computing n-dir is computing the numerical derivative of the function x cubed at x equals 2. Let's take a look at what that would be on the calculator. I've put the key steps for you up here, and what I want to point out is by hitting the math key followed by the 8 key, that's what will give you the n-deriv. Now, in the book that you're using, it's called n-dir. However, on this calculator, which is the TI-84 Plus Silver Edition, they've renamed it as n-deriv. But it's the same thing, n-dir or n-deriv. Then the rest of this is plugging in the x cubed, which is those functions, then the comma, then our x, and then finally plugging in the point 2. And what it gives us is a printout of 12.000001. So it's a very good, accurate, fairly accurate representation of what the derivative is. Now, we can also use n-dir or n-deriv to graph the derivative of a function. And so I want to show you how you'd plug in to your calculator if you want to use n-dir to graph the derivative of this particular function. And if the function we're going to do is y equals x times the absolute value of x divided by 2. And if possible, by looking at the graph, see if you can identify what the derivative function is. So now, on the calculator, this is what it would look like. You first need to enter into your equation editor mode. So you hit the Y key. Remember, the math 8 is what gives us the n-deriv. Then I need to plug in x, which I do right here, times, and then the math here with the combination here is what gives me the absolute value, and then I plug in this x right here. Then, of course, I have to do the divide by 2. Now, remember I said it takes 3 arguments? Well, that first one up to this point right here is the function itself, y equals x times the absolute value of x divided by 2. But now what we need to do is tell it what the variable is that we want to take the derivative with respect to, and that's x. Now, in the example I did earlier, we used the value of 2 to evaluate the numerical derivative. But here what we really want to do is have it evaluated over the whole domain of x. And that's why instead of putting a number in, we put x in a second time. So that's the x the first time, and then x the second time. Those are our 3 arguments. And now let's take a look at what the window would look like when you graph this. You get this graph right here. And if you recognize it, yes, in fact, that is y equals the absolute value of x. So that is the derivative of that original function. Let's move on to look at another theorem that connects differentiability to continuity. Theorem 1, if f has a derivative at x equals a, then f is a continuous at x equals a. Note, this theorem says that if a function has a derivative, then it is continuous, not the other way around. And this idea leads us into another theorem called the intermediate value theorem for derivatives. And what this theorem tells us is if a and b are any 2 points in an interval on which f is differentiable, then f prime, the derivative, takes on every value between f prime of a and f prime of b. Let's try an example that will illustrate the conditions that are necessary for the theorem. Does any function have the unit step function as its derivative? So here's the unit step function drawn on through the calculator. And of course, the answer is no. Because if you choose a value of a that's less than 0, then u of a, the unit function of a, is of course -1, because that's right here. And if we choose a value for b which is greater than 0, then we get u of b is +1. And what that means is that even though you get those 2 values, u, the function, doesn't take on any of the values between -1 and +1. Okay, well now it's time for you to try a problem. I want you to show that the function given below is not the derivative of any function on the interval in question. And the function is, the interval is from -1 to 1 inclusive, and the function f of x is equal to 0 when x is between -1 and 0 inclusive, and f of x is equal to 1 when x is greater than 0 and less than or equal to 1. Pause the video while you work on this problem. When you're finished, restart the video to check your solution. Welcome back. Let's find out how you did on this. What I would recommend is we choose a value for a that is in this range, this interval. And we'll choose a value for b, which is in this interval. Well, what's f of a going to equal? F of a is going to equal 0. And what does f of b equal? F of b would have to equal 1. But f does not take on any values between 0 and 1. So the function f of x does not satisfy the intermediate value theorem. Okay, so in this lesson, we looked at derivatives, the intermediate value theorem, and how you could apply that to look at when a derivative fails to exist. And we examined 4 instances in which that were true. So be sure to work the exercises that your teacher assigns, and we'll see you next time.